System design is the backbone of any successful software application. It's the blueprint that determines how different components interact, handle data, and serve users. A well-designed system ensures efficiency, scalability, and maintainability. Without it, even the most brilliant code can crumble under pressure. Think of a skyscraper. A strong foundation is crucial for stability and growth. Similarly, in software, a robust system design supports a seamless user experience and allows for future expansion. This essay will delve into the fundamental concepts of system design, drawing examples from industry giants like Netflix, Amazon, and Google. We'll explore essential components such as load balancing, caching, and microservices, highlighting their significance in building scalable and reliable applications. Furthermore, we'll touch upon back-end development essentials like API design, database selection, and authentication protocols. Finally, we'll delve into coding best practices, emphasizing the importance of clean code, design patterns, and optimization techniques. By the end of this essay, you'll have a solid understanding of the core principles of system design, equipping you to build robust and scalable software applications. Imagine a single server trying to handle millions of requests simultaneously. The result? Overloading, crashes, and frustrated users. Load balancing solves this problem by distributing incoming traffic across multiple servers. Think of it like a restaurant with multiple waiters. Instead of one waiter handling all the tables, load balancing ensures that each waiter or server gets a manageable number of customers or requests, preventing any single waiter from being overwhelmed. Load balancers act as traffic directors, routing requests to the least busy server. This ensures optimal resource utilization, prevents bottlenecks, and improves overall system performance and reliability. There are different load balancing algorithms, each with its strengths and weaknesses. Choosing the right algorithm depends on factors like traffic patterns, server capabilities, and desired levels of fault tolerance. Caching is like having a shortcut. Instead of fetching data from the main source every time, frequently accessed information is stored in a temporary storage area called a cache. This speeds up data retrieval and reduces the load on the main database or server. Think of it like keeping your most used tools within arm's reach. You don't have to go searching for them every time you need them. Similarly, caching brings frequently accessed data closer to the user, reducing latency and improving application responsiveness. There are different levels of caching, from browser caches to content delivery networks or CDNs. Each level serves a specific purpose, optimizing data delivery for different use cases. Effective caching strategies significantly enhance user experience by speeding up page load times and improving overall application performance. Microservices architecture is like building with Lego blocks. Instead of creating a single monolithic application, the system is broken down into smaller, independent services. Each service focuses on a specific functionality and communicates with other services through well-defined APIs. This modular approach offers several advantages. Individual services can be developed, deployed, and scaled independently, allowing for greater flexibility and agility. If one service fails, the others can continue operating, enhancing system resilience. Netflix, for instance, utilizes a microservices architecture to power its streaming service. Different services handle tasks like video encoding, recommendation generation, and user authentication, working together seamlessly to deliver a seamless streaming experience. Scalability refers to a system's ability to handle increasing demands. As the number of users, data volume, or traffic spikes, a scalable system can adapt and expand its capacity without compromising performance. There are two primary types of scaling: vertical and horizontal. Vertical scaling involves adding more resources to an existing server, such as increasing RAM or CPU power. Horizontal scaling, on the other hand, involves adding more servers to distribute the workload. Choosing the right scaling strategy depends on factors such as cost, complexity, and the nature of the application. Cloud computing platforms have made it easier than ever to scale applications dynamically, adjusting resources based on real-time demand. Backend fundamentals, APIs, databases, and security. The backend of an application is like the engine room of a ship. It's responsible for processing data, handling business logic, and managing interactions with the database. Key components of backend development include API design, database selection, and authentication protocols. APIs, or application programming interfaces, act as intermediaries, allowing different software components to communicate with each other. Well-designed APIs are crucial for building robust and maintainable applications. Databases store and manage application data, and choosing the right database depends on factors like data structure, query patterns, and scalability requirements. Authentication and authorization mechanisms are essential for securing user data and preventing unauthorized access. Strong passwords, multi-factor authentication, and secure communication protocols are crucial for protecting sensitive information. Lessons from giants Netflix, Amazon, and Google. Industry giants like Netflix, Amazon, and Google have revolutionized system design, developing innovative solutions to handle massive scale and complexity. Netflix, for instance, relies heavily on a microservices architecture, allowing them to scale their streaming service to millions of users worldwide. Amazon, with its vast e-commerce platform, utilizes a distributed database system to manage massive amounts of data and ensure high availability. Google, known for its search engine and cloud services, has developed sophisticated load balancing and caching mechanisms to handle billions of search queries and requests. These companies exemplify the importance of building robust, scalable, and resilient systems. Their architectures prioritize flexibility, fault tolerance, and continuous innovation, serving as valuable case studies for aspiring software architects. Clean code, design patterns, and optimization techniques. Writing clean, maintainable code is essential for any software project. Clean code is easy to understand, modify, and extend, reducing the likelihood of bugs and making collaboration smoother. Design patterns provide reusable solutions to common software design problems. They offer proven approaches to structuring code, improving code organization, and promoting reusability. Optimization techniques aim to improve code performance, making applications faster and more efficient. This can involve optimizing database queries, reducing network requests, or implementing caching strategies. By adhering to coding best practices, utilizing design patterns, and employing optimization techniques, developers can build high-quality software that is both robust and performant. Insights from Intel and final thoughts. During my time at Intel, I witnessed firsthand the critical role of system design in building high-performance computing systems. From designing complex chip architectures to optimizing software for parallel processing, every aspect revolved around creating efficient and scalable solutions. The principles of load balancing, caching, and distributed systems were paramount in maximizing performance and ensuring system stability. We learned the importance of designing for fault tolerance, anticipating potential bottlenecks, and continuously optimizing for efficiency. In conclusion, mastering system design is an ongoing journey. It requires a deep understanding of architectural principles, a willingness to adapt to evolving technologies, and a commitment to writing clean, efficient, and maintainable code. By embracing these principles and learning from the successes and failures of others, we can build software that is not only functional but also scalable, reliable, and future-proof.